Hi, folks. People here. Hello, hello. Sorry, I accidentally started it in physics 2, and I was like, oh, I wonder why no one's here. Hello. All right. See people, is anybody here on Twitch? Looks like, hello. The last day of class for us. Oh my gosh. I'm sure you're all excited, ready for it to be done. It's probably the most accurate. Sorry. So hopefully everybody saw the quiz and the test 3 self-assessment. Let me know if you have any trouble with those. Hello, hello. All right. Okay. A week-long break, then you can start physics 2. Yay! That sounds exciting. Okay. So I'm gonna pull up OneNote. So our agenda for today is to finish the last of physics 1, which is some torque related stuff. Okay, let me pull this up. If I can find where I put my notes. Maybe not. Should be in here somewhere. There it is. I knew it was in here somewhere. Ooh. All right. So just a quick recap what we were doing in class. Last time we were talking about finding the torque, our F sine theta. So it is a force that is acting off the axis. And then, so we have F is the force. We have R is the distance from the axis to the force. And then we have theta, which is the angle between our R vector and our F vector. Sorry. And we did a couple practice things. And we talked about net torque. So to get net torque, you add them up and you have to keep in mind the signs, whether it's trying to make the thing turn clockwise or counterclockwise. Okay. So we're going to pick up right there and talk about equilibrium. Looking for the right stuff. Yeah, that's boring. Okay. Oh, hello. So, fold this down. Oh gosh. I'm very sorry. I even drank coffee, which I never do. Oh. Okay. Add up all the torque. With the correct signs. And you get oh gosh. You get the net torque. Okay. So if you think back to several chapters ago, we would find if we added up all the forces, we would get the net force, right? And then if our net force is equal to 0, that was equilibrium, right? Equilibrium meant that it was not accelerating. That it was either stationary or it was moving with a constant velocity, right? So stationary or pen fail. There we go. Constant velocity. Okay. And specifically, if it's stationary, that was static equilibrium. Hopefully all of this looks familiar. We're going to add a new definition. So static equilibrium means that it is stationary and staying that way. It means that the sum of all the forces in vector form is 0. It also means the sum of the torques is 0. So this means it's not accelerating and it is not rotating. An example of this might be, let's say we have a seesaw. Right. Some high quality examples here. So we have our fulcrum. We'll say the seesaw is, let's see, 4 meters long total. And let's say we have a small person, very small person, standing at one end. Small person on one end. It has a mass of, let's say, 50 kilograms. So by small person, perhaps I mean child. That would be a logical thing. And say they're all the way at the end. And let's say we have a larger person at the other end. Okay. They're just standing on it because that's how seesaws work. So, tell me what's going to happen. There you go. They're almost the same size, and one of them has twice as much mass. So thick does sound like a better idea. So if they just started out like this, I had a small person here and the same, or my larger person here, what would happen? Seesaw will bob up and down until it reaches equilibrium. Okay. Do you expect equilibrium to look like this? Or how do you think equilibrium is going to look? No. Heavier person will be further down. We can probably expect the heavier person to be resting on the ground, right? Like this. Makes sense, right? If you've ridden a seesaw with a much smaller person, it's probably going to look like that. Okay. So I'm going to declare this to be 20 degrees, right? That has to do with how high this fulcrum is, right? So can you tell me where the axis of rotation is? In the middle. Yep. It's where it's attached to the fulcrum. Okay. Can you tell me what are the forces acting on the seesaw? Normal, force of heavy person, force of lighter person. Okay. And also the weight of the seesaw itself. We're going to go with frictionless for our fulcrum here. So we have the weight of the seesaw. We have the weight of the smaller person. We have the weight of the larger person. And we have a normal force. Tell me about the normal force. Where is the normal force acting? Where the seesaw touches the ground and at the fulcrum. So we have a normal force here and a normal force here. Right? If we were to remove the ground, this would keep rotating until it was completely vertical, right? So the ground must be holding up a little bit. Right. So we have two normal forces, one at the fulcrum wouldn't it change as it is moving? We're dealing with the point when it's done moving and it's just like stationary. Yeah. Does that make sense? Okay. So we had our 50 kilogram person times 9.8. We had our 100 kilogram person times 9.8. We have our weight of the seesaw. I'm going to say the seesaw has a mass of 25 kilograms. So it's just 25 times 9.8. Okay. So here's all our forces. If I asked you to find the force here, you would run into a problem. Because you're like, okay, I know all of the forces have to add up to 0. Okay, so I have the weight of the seesaw, the weight of the small person, the weight of the large person, the normal at the fulcrum, and the normal at the end equals 0. But I have two unknowns. So how do I solve this? I solve this by knowing that my torque also has to equal 0. So if I think about my seesaw, what are the torques? Acting on it. So each of these forces could be exerting a torque, but it might not be. So we have weight, seesaw, weight, small person, weight, large person. These are our forces: normal, fulcrum, normal. Which one of these exerts 0 torque? Okay, we'd have torque from both people. Are any of these going to be 0? Normal at the fulcrum. Why? You're correct. No radius. There you go. Good. So this one's 0. How about any of the others? There's one more. Yes, the weight of the seesaw. Because the weight of the seesaw acts at the center of mass. The center of mass for our seesaw that is equal lengths on both edges is going to be the force of gravity acting down right there. So this one is also 0. Good. Okie dokie. So we have 3 torques. We have a weight from the small person, a weight from the large person, and a normal force at the end. So can we find these torques? So the weight of the small person, FG small person, right, was what? It was 50 kilograms times 9.8. So this is 490 newtons. So the torque from the small person is F RF sine theta. Okay. F is 490 newtons. What's R? And what's sine theta? I decided it was 4 meters long in total. So my R is going to be 2 meters. And I decided this is 20 degrees. So what is my angle theta? What's theta going to be? 70 degrees. Looks like it's going to be more than that. 20 plus 90, 110. But due to symmetry, you'll probably get the same answer. So we do 490 times 2 times the sine of 110 degrees. Yep. So I get 921 Newton meters. Is this positive or negative? Okay. Michael says negative. Why negative? You are correct, but it's the torque is in a clockwise direction. Clockwise direction is negative. Okay. All that making sense? Okay. What about the torque for the large person? Or F sine theta, 2 meters. This is 100 kilograms. What's theta in this case? It is this is R, this is F. So the angle between them, so this one is 70 degrees. It ends up being the other way around. But you get the same number either way. Times 2 times 980. Okay, so I get 1842 Newton meters. Is this one positive or negative? Positive. Yep. Because it's making it go counterclockwise. Okay. So now what? I know that my torques have to add up to 0. That's not what I meant to do. I know that my torques have to add up to 0. So sum of my torques equals 0. So that is my torque from my small person, negative 921, plus my torque from my large person, plus my torque from the normal force at the end. So the torque from the normal force at the end is going to be negative 121 Newton meters. I think this is because it's precisely twice the mass. It wouldn't necessarily be the same if it wasn't precisely twice the mass. Right? And it's negative. Does that make sense? Hopefully, yes, because we have a negative torque this way, a positive torque this way. They're both down, but one's positive, one's negative. And then we have a negative torque from the normal force here. Okay. All this making sense? Woo. Okay. So can we find the magnitude of the normal force? Well, that would be our torque divided by r sine theta. So it would be 921 divided by r is the 2 meters. Sine theta is, let's see, our normal force is straight up. It's perpendicular to our, like, the ground is pushing up. It's perpendicular to the ground, if that makes sense. And our r is like that. So this is our 110 again. Doesn't really make a difference. Divided by 2, divided by 490 newtons. Okay. So we have 980 down here, 490 up here. We have 490 down here. Can we find the normal force for the fulcrum? We also would need to find the weight of the seesaw, which would be 20 times 9.8, 196 newtons, weight of the seesaw. Okay. So the normal force at the fulcrum is going to be such that if we had, now we're going to do regular x and y, right? We have 980 down plus 490 down plus 196 down plus 490 up. These will cancel. Plus our normal force up equals 0. So we end up with 80 plus normal force at the fulcrum, 1176 newtons. Does this make sense? So it's somewhat the same as our previous situation, except now we're doing some of the torques as well as doing some of the forces. Okay, so this is sort of the classic static equilibrium problem. Which is like people standing on some structure that has some supports, and you have to find, like, you might have to find, like, where is this person standing? Or you might have to find the force, the normal force in each support. Might not be the same. If you've ever carried a really heavy object with someone, especially a really heavy object like up or down stairs, right? Right. And you have this debate about who's carrying more weight, right? That's a classic static equilibrium problem. So one important thing about this, both of these really, where's the axis? You're always finding torque about a specific axis, and it has to be the same axis for all of our torques. But in this case, where we just have two people standing on a structure, where's our axis? So the rule here is that if it's stationary, you get to pick. Yeah, there is none, kind of, yeah. For static equilibrium, you get to pick. And it does not have to be the regular expected one, right? So for example, we did this whole problem using this as our axis. We could very easily do it using this as our axis, right? It's weird, but there's no mathematical reason you can't do this, right? I mean, it is also not rotating about that axis. The net torque about that axis also has to be zero. So our forces, the weight and the normal at this end both have no torque. We would have torque from the weight of our seesaw and our normal force, which we found was 1176. And then we had our 490 out here, right? Real quick. Yeah, let's make sure it works. Yeah. So I can say, okay, I have a torque from this large person is zero. The torque from the normal force at the end is zero. The torque from the weight of the seesaw is now the weight of the seesaw times the sine of the angle. The torque from the normal at the fulcrum will be our force times 2 times sine 110. The torque from the weight of the small person is going to be 490. Now it's at 4 meters from our fulcrum, our axis. This one's 110, doesn't really matter. Are any of these positive or any of these negative? This one is still going clockwise, so negative. This weight is to make it go clockwise, that would be negative. This weight is to make it go counterclockwise, that would be positive. If we add all these up, you get zero. Torque is still zero about any axis. So when you have a question like this, right, you could say, oh, is it rotating about this point? Is it rotating about this point? You can pick either. You can do both, and you can solve the problem that way. Does that make sense? Usually you'll have to do at least 2 axes. Two axes, or you have to do torque and force both to solve a problem. Right? I could use this tactic to find this normal force right here. Instead of doing the net force like I did up here. Either one should work. Those are kind of your 2 options. Right. Questions about any of this? So static equilibrium always gives us 0 net torque. Yes. That is a good way to put it. Static equilibrium means F net equals 0 and tau net equals 0. Wait, 3 no's. What are those no's about? No, it doesn't make sense. No, this isn't true. I forget, did I ask a question? Tell me what your no's are about. Switch to less eye-bleeding color here. No questions. Okay, good. It's like, no, you don't have any questions, or no, it doesn't make any sense. Okay, that's good. All right, static equilibrium, check. What if the net torque does not equal 0? What's going to happen? Find all the known torques and solve for the unknown one. I mean more in terms of a physical sense. So if I had a structure where the net torque is not equal to 0, is it going to be in static equilibrium? It's going to rotate. Specifically, it will rotate. But really, it's not just about rotation, just like F net does not equal 0. It moves, but that's not the most accurate way to talk about it. The most accurate way to talk about it is to say that it accelerates. A does not equal 0. For torque, the most accurate thing isn't to say it rotates, it's to say it has an angular acceleration. Angularly accelerates. Alpha does not equal 0. Okay. So we talked about this really briefly way back. Way back. Here. We talked about there's 2 equations for torque. So far, we were talking about the cause equation, that how we figure out the torque that is being applied. There's also the result equation, which is what happens, the angular acceleration that occurs. So now we're going to talk about that result equation. There we go, right? So we have F net vector form is mass times acceleration. We're going to stick this in scalar form for now, I times alpha. So we have acceleration, we have angular acceleration. Can you tell me what units this is going to be? What are the units for angular acceleration? John, remember it's acceleration, not velocity. Radians per second squared. Okay. So this is acceleration in meters per second squared. This is mass. This is, you can kind of think of it like angular mass. If that helps you, there's mass times acceleration, there's angular mass times angular acceleration. Yeah. I is something called the moment of inertia. Moment of inertia. Okay. What does moment of inertia mean? Moment of inertia has to do with how easy something is to spin. You can think of regular mass has to do with how easy or how hard it is to accelerate something, right? If I push with 5 newtons, am I going to get 1 meter per second squared or 10 meters per second squared, right? Has to do with how massive the object is. The same thing is true for moment of inertia. It's a measure of how hard it is to spin something. Now, this is really unfortunate because there is a great lab for this, where you can really feel it and feel the difference that the distribution of mass makes. But sadly, yeah, you can't. Sorry. So this has to do with the mass, right? It has to do with how the mass is distributed. And it has to do with the axis. So this is a really weird thing for students to kind of wrap their heads around, is you think like, okay, mass is mass. If it's 2 kilograms here, it's 2 kilograms on the moon, it's 2 kilograms. If I'm tossing it in the air, it's 2 kilograms. If I'm like contact juggling with it, I don't know. Moment of inertia depends on what you're trying to do. It depends on how you are spinning it. So give me a sec. I'm going to go get my broom because I feel like that's a really good demo for this. Do not judge that I'm wearing pajamas. I'll be right back. All right. I'm trying to make my video bigger, sorry. Can I make this bigger? I want you to see my lovely face.
question. Why can't I see this video on here? I mean, this is really judgmental of them to presume that you're not like trying to see. No, that's not what I wanted. I can't make my face big. I should have been recording. Dang it. If you know how to do this, tell me. I'm trying to make this. I'm sure you can do it on your machine. I'm trying to do it on this machine. I don't know if I can. Let's try this. Oh, it's not working. Boo. Oh, darn it. You would think they had an option for this. Nope. Aw. Okay. Well, that sucks. Oh. It comes up for a second and then it disappears. That's so weird. Can you make my picture bigger? People who are on Teams? People who are on Twitch, I think you might just be stuck. Okay. So here's a broom. I've left the dustpan attachment attached in order to provide a different amount of mass. Okay, if you're on Teams. Okay, so where's the center mass? It's right here, because that's where it balances. Right. So I can rotate it about that center mass. Bonk. Bonk, right? But I can also, ooh, I tried right clicking, but pin doesn't come up. Comes up for other people, not for me. Yeah. Yeah. It's not designed for what I'm trying to do here. It's like, why are there two of you in this meeting? That's so bizarre. Okay. Okay. So imagine the sort of the alternative, right? I am trying to rotate it around just the ends. If you have a broom, I recommend trying this. It's really hard. Right? Why is that? It's the same mass. So why is it harder to rotate like this versus like this? Right? This is easy. This is hard. Oh, like destroying my apartment here. Same math. What did I change? I changed the axis. Right. I could also change the distribution of mass, right? By taking my dustbin attachment and moving it to a different place. So the further the mass is from the axis, the greater the moment of inertia. Okay. And we express this by saying for a point mass. So like if all of the mass, it's like a ball or something that is heavy on like maybe a very light stick or a very light string, you can basically pretend that it's all the mass in one little dot. Your moment of inertia is the mass times the distance. This is not the radius. It's not like the radius of a circle. This is the distance from the axis squared. Right. If you have more than one, your moment of inertia is m r squared for each of them. With more weight being on opposite side of the axis, more force to counteract the difference. Yeah, kind of think of it that way. So the classic example for this is if you see figure skaters, right? This is more about angular momentum, which we're going to talk about later. But if they have all of their arms out and then they pull their arms in, they go faster, right? The reason is conservation of momentum, but what they're changing is their moment of inertia, right? Mass is the same, different moment of inertia. Sort of like a really quick example. You had a thing that was like this on the quiz from last week, and it asks you to find the center of mass for where this is. So I forget where it is actually. It's like in here somewhere. But you might be asked, like, if it's rotating about this one, what is its moment of inertia, right? M1, M2, M3. It would just be M1, X, M2, Y, M3 times 0. Because this is so teeny, we basically pretend that it's all in a single point. This is why monster hunter weapons are impossible. Too much torque needs to be applied in order to swing them. Is this a specific type of monster hunting weapon? I mean, this is why if you have something like a glaive, you don't want a super massive blade at the end of a very, very long pole. I mean, you get more force, but it's really difficult to maneuver. Right? You might even want to put like a counterweight at this end. Okay. I realize I've only got 15 minutes left, so I want to talk a little bit, maybe a little bit faster. So what if you have a large extended object? So for example, that broom that we were talking about, so, or like something more complicated, although that's pretty complicated, isn't it, as it is. What would you do? Is this a game or an anime? Those are like the two choices I feel like you're talking about here. Great swords for monster hunting. So what you would do is chop it up into little bits, and then you would integrate over those little bits. I am not going to do an example because we're not going to make you do it on a test. Oh, it's a game. Okay. Is it just called Monster Hunter? So there are basic shapes that have pre-calculated moments of inertia. Where is the front of the sheet? Oh, it's in the other class. That's why. I'll find it. They haven't changed it in a while, so it's in like an old folder. There we go. And I said to share my screen. There we go. All right. On your formula sheet, you might notice this. These are the very tiny moments of inertia for all these different shapes, right? So for example, we have this thin rod about the end. There was a question. We're just going to do a really simple one. A question from the quiz. Involving you sitting on a branch at the end, and it asked you to find the net torque. Right? I don't remember. Oh, you can't see this. Sorry. Asked you to find the net torque, right? So you found your force of gravity due to the branch itself. You found the force of gravity due to the guy. You did radius, you did tau equals those two for weight of the branch plus tau weight of the person. Hopefully this looks familiar. If not, let me know. So the question might be, if it breaks at the joint to the tree, what is its initial angular acceleration as it starts to fall? So we're going to presume that this is going to rotate around, that it's not going to fall straight down. It's just going to like crack, right? So the whole thing is going to swing down like that. So let's say, I don't know, our net torque was, I don't know, some value. So what we would do is we would find the moment of inertia for this whole thing of the branch plus the person. So that would be the moment of inertia for a long, thin rod rotating about its end. Just show my desktop. This is easier. Maybe. There we go. Right. I have two options for the branch. It could be a thin rod rotating about its center or a thin rod rotating about its end. Notice that I have a different moment of inertia in each of these cases. Right? It is a lower number if it's rotating about the center than if it's rotating about the end. Just like the broom, right? The more mass that is further away from the center, the more moment of inertia I have. So I'm going to use this equation, 1/3 ml squared. So this is I branch plus I person. So this is going to be 1/3 mass of the branch, length of the branch squared, plus for the person, I'm going to treat them just like a blob. So it would be the mass of the person times their distance, which in this case is the length of the branch squared. And then I would do tau equals I alpha. This number is going to be in Newton meters. This number is going to be in kilogram meter squared. That's a super weird, sorry, Twitch lagged for a second. That's a super weird unit. But what do I get for alpha? So alpha is a Newton meter divided by a kilogram meter squared. A Newton is also known as a kilogram meter per second squared times meters over kilogram meter squared. Kilogram cancels, meter, 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 meter. I end up with alpha is per second squared, which is why I can stick radians in there, because radians is a magical unit that just appears when I need it. Radians per second squared. Okay. All this making sense? All good? Yep. I know I'm going really fast. We have like 10 minutes left. So we can think about everything that's like translational has like a rotational counterpart. So where we had mass, now we have I. Where we had A, now we had alpha. Where we had force, now we have torque. There are more, right? There is, you know what, I'm not going to talk about that. That's okay. What are some other things? Well, when we have velocity, we have angular velocity. That's one that we know. We can have momentum. We can also have angular momentum. And these can both be conserved. This is that figure skater idea, that angular momentum is conserved. I'm not going to talk about it a huge amount. I'm just going to kind of show you the... So this is mass times velocity. Can you guess what it is for angular momentum? So look back, if m is the same as I, close. L equals L. There you go, I omega. You are correct. So when the figure skater changes her I, if L is the same, she's going to change her omega. You also have kinetic energy, 1/2 mv squared. You also have rotational kinetic energy. This is going to be, can you guess? Can you come to a rational conclusion? One half I omega squared, you are correct. So there is a great problem that you see a lot, which is something like you have like a string that's attached to a weight and it's wrapped around like a pulley that has mass. And then you allow this to drop, right? This is a really classic problem And one of the easiest ways to do it is to think about it in terms of energy. That you have some amount of potential energy due to the height of your bucket, right? Where does that energy go? It goes into the kinetic energy of your bucket, speeds up as it drops, but you also have to spend some of that energy to make the pulley rotate, right? So your I in this case would be I probably for either a cylinder about the center, or maybe, yeah, I mean, it could be a sphere, but that's weird. I don't know why you'd want a spherical pulley. So probably a cylinder, so you'd do 1/2 mr squared. So your mgh would be 1/2, it's mv squared plus 1/2. This was 1/2 mr squared, where that's the mass of the pulley and the radius of the pulley. Pulley, radius of the pulley. So that's my I. So then it would be 1/2 I omega squared. We know that V equals R omega. We then would know everything and we can solve for V. In this case, this would be R omega. Because the speed that this is going down is related to the speed that the rope can come off the pulley. So it would be this radius R omega. Okay. Let's see. I'm looking to see if there are any other bits and pieces. We're not going to do rolling. We're not going to do too much with angular momentum. The only other thing, any questions about this? I know I'm going really fast. I just want to make sure you have the opportunity to see it. So if you have access to the textbook, the relevant chapters are section for torque 1, definitely 2, definitely 3, definitely 4. We skipped parallel axis theorem, but you should look at it anyway. 5, 6, 7, 8. But we are going to skip 9. 10, I'm going to make a video, I think, about for cross product. No 11 and no 12. Okay. So 10 is about the vector cross product. I think I want to make a video, but it's also really difficult to do this without being able to show you my hands, because it's all about doing the right hand rule. So we have already talked about a couple of right hand rule things. So we talked about the omega is when you wrap your fingers, and then your thumb is positive or negative, right? So if you're looking at a record that's rotating, if it's rotating clockwise, you would wrap your fingers. That means there is a negative omega, right? You can also call that a vector. So clockwise is negative, but you can also think of it as like that downward vector. And you can do the same for like if it's a clock on a wall, it's rotating clockwise, your thumb would be going into the wall. Right. Does that make sense? Right? Instead of just thinking about it as being plus or minus, think about it as, oh, this one's out at my face. This one is up. This one is, oh, it's sideways, right? So your torque vector is going to point in the same direction as your alpha vector. So just like F equals ma is vectors, this is really properly vectors, right? So if you have a, if we think about that pulley, right? There is a torque on that pulley because there is a force of this weight pulling down at this radius r. That torque is in the downward direction, right? Or that force is in the downward direction, I'm sorry. So your alpha ends up being counterclockwise, which corresponds to a vector coming out at your face. Alpha vector out at your face, which means my torque vector must be out at my face. These two are going to be in the same direction. To get your torque vector, that is the cross product. I don't know if I have time to talk about this. I'm going to keep going. If you need to leave, you can leave. Sorry. It's saved anyway on Twitch. So cross product. So for any cross product, A cross B, the magnitude is AB sine theta. Well, hey, that looks like R cross F. The magnitude is RF sine theta. The direction is given by a right-hand rule. So the way right-hand rules work, your thumb cross your index finger equal bird. So if you have an R that is to the left, you have an F that is downward, your middle finger is out of the page at your face, which is what we got out of the page at your face. Okay. So you hold your hand like this. Thumbs up. Finger gun. Answer. Okay. So the reason I'm trying to squish this in at the very end of the semester is that this is a big thing in physics too. Not immediately, but when you get to the magnets, it is like all cross products all the time. So I just kind of want you to get an introduction to it. So if you have me or another professor and they'll say, you've seen cross products, you'll be like, oh yes, I've seen cross products. I'm going to stop here and I will try to make a little video with some more information in it for you. that goes into a little more detail because this is really rushed. But yeah, so that concludes Physics 1. Thank you all so much. I'm sorry that this semester's been so weird. Hopefully y'all are doing okay. Please tell me if you're not. I've had a lot of people. There's not a whole lot of people who are watching these live, which makes me a little hesitant, especially because people didn't do so hot on test number 3. Yeah. I'm going to be posting a bunch of resources to help you study. There's some PowerPoints, some practice problems, a final homework, things like that. And so stay tuned. I'm going to do some review during the reading days. I'm going to do some review during the finals week leading up to the final. I feel like it's on Monday or something. I'm not sure. But I'm going to try hard to help you all out. Please definitely ask me if you have questions about things. Yeah. Would I mind doing a question from the quiz? I might not do it, but I'll talk about it. What was the question? Let me see if I can pull it up. Oh. Which one was it? First question. Okay. The first question, I think the challenge is more figuring out. The question was at what distance from the center of the 2 kilogram ball? Oh, hi, Eden. You have good summer too. I didn't know you were here. Oh, no, there you are. There's like couple chats earlier up. So you had a ball and it had a radius of 2 centimeters. Let me draw this bigger. And then you had a 1 meter. I don't think it specifies. The 1 meter long rod is from the end to the end. Right, so from center to center, it would be 104 centimeters. I'll see you later. Bye. And then the question is asking how far from the center of this. So you can make this your, you get to decide where 0 is. You can make 0 be right here. So then this would be 2. This would be 52. This would be 102. This would be 104. So then when you do your mass times your x plus your mass times your x plus your mass times your x times your total mass, right? One of these is 0. One of these is 52. One of these is 104. And then the value you get should be the distance from 0, which is the point you're trying to measure. If you choose 0 to be right here or like right here, you can absolutely do that. Totally fair. The only thing you have to remember is that you're going to get an x value from there, and then you'll have to do, okay, from here to here is 106 minus x. Is that right? Because this is 2, 4, 104, 106. Yeah. Okay. Right. Sounds good. Might try to do another one for today. All right. Thank you to Nate. Everybody have a wonderful last couple days of classes. Have great reading days. I will see you to practice for the final. Yeah, good luck. Bye.